I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Last time, we solved problem number 31 in Standard ML, the first ML dialect we've used. We also discussed several of the nice features of Standard ML's type system. Today, I want to continue that discussion and talk more about how Standard ML code is written, typed, and organized. As a reminder, Standard ML is a mostly pure functional programming language. That means that most values in Standard ML are immutable, but there are a few types that intentionally break this rule. We already mentioned one mutable type last time, the type of arrays whose elements can be changed in place. There's no built-in special syntax for arrays in Standard ML. The easiest way to construct an array is with the array.fromList function, which converts a list into an array. There are also a few other helpful constructors. Array.array takes an integer and a value and creates an array of the specified length, where every element is equal to the specified value. And array.tabulate calls a function for each index to figure out what value to place at that position. The other major mutable type is the type ref. Ref is the type of mutable reference cells. An aref for some type A contains a single value of type A. You can think of it as being like a non-null unique pointer in C++ or a box in Rust. Crucially, although most values in ML are immutable, a ref can have its contents reassigned, similar to array elements. Construction of a reference cell is done with the ref function, which takes a value and returns a brand new cell containing that value. Note carefully, this function has type A maps to aref, but it's definitely a cheater. If we call this function twice with the same value, it'll give us two distinct reference cells, which violates referential transparency. Put another way, if Standard ML didn't give us a list type, we could define one of our own, even if we didn't get the convenient syntax sugar for list construction. But if Standard ML didn't provide the ref type and corresponding function, we couldn't possibly write something equivalent, since it violates the normal rules of the language. We can pass around a ref cell just like any other value. Standard ML values are never implicitly copied, so if we pass a ref to a function and that function modifies the cell's value, the caller will also see the modification. Speaking of which, we can access the value of a ref cell with the prefix bang operator, and we can assign to a ref cell with the infix : operator. This gives us a limited form of mutability in a functional program, while clearly marking the parts of our program that can be mutated via the type system. Next, I want to briefly discuss error handling. Most ML dialects come with some form of runtime exceptions, which should look pretty familiar if you're coming from C++, Java, Python, or any other language that takes the conventional approach to exceptions we see all the time today. It's worth noting, though, that Standard ML, while supporting a fairly typical exception implementation, does try to avoid using them unless necessary for correctness or ergonomics. Instead, in many situations, Standard ML prefers to return an appropriate data type, often an option, to indicate the possibility of failure statically in the type system. As a concrete example, consider Python's built-in list.index method. This method returns the index of a supplied value in a list, or the first such index if the value appears multiple times. If the value is not found in the list, Python raises a value error and expects someone else in the call stack to handle the problem. The closest analog in Standard ML is vector.findI, which takes a predicate and returns the first matching element as well as its index. But the return type of vector.findI is an optional tuple. If such a value exists, then a sum value will be returned containing the matching value as well as its index. But if not, then this function simply returns the special constant none, which requires that the caller explicitly deal with the possibility of absence. That being said, Standard ML does still support traditional exceptions and uses them when an optional return type would place undue burden on the caller. For example, the function textio.openin takes a string file name and opens the indicated file for reading. But if the file does not exist or can't be accessed for security reasons, then textio.openin raises an exception, since the caller will, in most cases, simply want the program to fail in that extraneous circumstance. Custom exception cases in Standard ML are not declared with the data type declaration. Instead, a new exception case is declared with the exception keyword, followed by the structure of a single constructor. If the exception type doesn't need arguments, then the latter portion of the declaration can be omitted entirely, similar to zero-argument data type cases. Internally, an exception declaration adds a new case to the built-in type exn. This type is deeply magical and is the only type which is extensible in this way. We construct an exception value using the constructor function we just declared. Remember that this new exception value is of type exn, not of some newly defined data type. To raise an exception, we use the raise special syntax. Standard ML doesn't even try to pretend that this one is a function. Raise is a special keyword and must always be followed immediately by an exception value. To catch an exception, we use the handle keyword. Handle is an infix keyword which runs the expression on its left and, in the event of an exception, tries to pattern match the exception against the cases on the right. If any of the cases match, then we stop unwinding the stack and run the code in that block. Otherwise, the handle block has failed to handle the exception, and we continue propagating upwards. As you can see, this is a fairly basic implementation of exception handling. You're not going to find any higher order effect handling mechanisms in standard ML, since the priority of this implementation is simplicity. If you find yourself wanting to perform more complex sequencing with exceptions, you might consider using a proper data type instead. The next thing I'd like to briefly touch on is mutual recursion. As we discussed in the last video, standard ML functions declared with the fun keyword have no problem being recursive. This was our naive implementation of a recursive factorial function. Notably, the word factorial can be invoked on the right-hand side of the equal sign, even though it's still being defined, because the name of the function is in scope within its own definition. If you're a Lisp programmer, you can think of the fun keyword as automatically behaving something like letrec for local Lisp bindings. However, aside from this one exception, standard ML bindings, and hence names, are introduced in the order they appear in a source file. This means that, similar to C, a function declared earlier in the file cannot reference a function or value declared later in the file. This presents a problem with mutually recursive functions. A set of mutually recursive functions is one where the functions call each other in a cycle. Many practical examples of this come from state machines or parsers, but the typical academic example of mutual recursion can be discussed with only natural numbers. The piano encoding of natural numbers defines a natural number either as the special constant 0 or as the successor of another natural number. That is, if we switch over to Haskell for a moment, we could define a data type using this representation like so. This may seem contrived, but this is the actual type used to define the natural numbers in proof-assistant languages like Agda, where it's critical to define numbers in such a way that we can perform mathematical induction on them meaningfully. With this encoding of numbers, we might endeavor to write a function that returns whether a number is even or odd. If we were using an ordinary representation of numbers, we would simply use the modulo operator. But in this case, we don't have an operator with that name. Let's write the isEven function first. Inside the function, we pattern match on its sole argument. If the value we were given is 0, then it's clearly even, because 0 is an even number. If it's not 0, then it must be the successor of some other natural number. Call that number x. Then the successor of x is even if and only if x itself is odd. The isOdd function looks very similar. We pattern match on the sole argument. If the argument is 0, then it's clearly not odd. If the argument is non-zero, then it must be the successor of some other number, which we'll call x. In that case, the successor of x is odd if and only if x is even. Notably, these two functions depend on each other. Neither one can work correctly unless both are present. In Haskell, this requires no special work, as declarations in a Haskell module can see all other declarations in the same module, regardless of where they appear. But if we try to do the same thing in standard ML, the isEven function will fail to compile, since the isOdd function it requires is not yet in scope. In C, we would fix this with a forward declaration. In standard ML, we link mutually recursive functions together by adjoining the declarations with the AND keyword. In fact, this isn't just limited to functions. Mutually recursive data types can be defined in the same way. For instance, we can define the type of a rose tree like so. A tree of A values consists of a root node, which contains an A value, and a forest. A forest of A values, in turn, consists of a list of tree nodes. Note again that both of these data types depend on each other. Neither tree nor forest can exist without the other one. With all of that out of the way, let's get on to the meat of why I'm making a second video on this language at all. To me, the most important thing that an ML dialect brings to the table isn't its type system, or its mostly functional approach to programming, or its sum of product data types. All of those are very nice, but the most important thing, in my opinion, that ML has given us is its module system. Most languages have a notion of a module or a package. In Haskell, for example, every file is automatically a module. Modules provide a convenient namespace into which to store our functions, variables, and data types, so that, for example, data.list and data.hashmap can both have functions called insert that work differently and take different argument lists. Note that I'm not talking about polymorphism here. The two insert functions that I just mentioned are genuinely distinct. The former takes a value in a list and inserts the value in sorted position into the list. This requires the element type of the list to be orderable by a total ordering. The latter takes a key, which must be comparable for equality and hashable, and a value, and inserts that key value pair into a supplied hash map. We can name them the same thing, since the module system takes care of name resolution for us, but they're clearly different functions with different purposes. Standard ML at a very superficial level takes a similar approach, except that modules are called structures, and we don't get one at the top level of our file for free. Note that I'm going to start calling these things structures from now on. If you're coming from a language like C or Rust, where the keyword struct initiates a data type declaration, you'll want to forget about that for the rest of this video. Data types in standard ML are always introduced with the data type keyword, and the word structure is taken to mean essentially what module means in Python or Rust. To declare a structure, we start with the structure keyword. Then we use a struct block to define its contents. The inside of a structure can contain any sort of declarations, including data types, exceptions, functions, values, and even other structures. Here's a slimmed down version of the option structure from the standard ML basis library. The The structure's name is option with a capital O. Inside, we define a data type called a option. Additionally, we define an exception, also called option, which is thrown if we try to extract the value from an empty option. Remember that an exception declaration adds a variant to the existing exin global data type, rather than creating a new one. So this line is not declaring a new type called option again, but is instead declaring a constructor called option for exceptions. Finally, we write some helper functions to work with the option type. Callers would generally refer to the names of this structure fully qualified. So the data type would be written as option.option, and the functions as option.map, option.isSum, and option.valof. We can import all of the names from a structure into the current scope with the open keyword. Or we can alias individual ones by simply redeclaring them as a synonym in a new scope. Now, in standard ML, a structure is just a type of declaration, similar in some ways to function or value declarations. Functions and values have types, and as it happens, structures have a sort of analog for types as well. The structure level analog to a value's type is the structure's signature. Our current option structure will have an inferred signature which exposes a data type, an exception, and 3 callable values. We can explicitly declare this signature like so. Notably, the signature is what the outside world sees, while the structure itself contains all of the implementation details, such as the actual behavior of the functions. If we were to omit one of the val lines from the signature declaration, that function would effectively become private in the option struct. The structure itself can see the function, but it's hidden from the outside world since it's not present in the signature. Another interesting thing that we can immediately do with signatures is hide data type implementations. Our current structure signature specifies that the option type has 2 constructors and tells us their shape. This allows outside callers to invoke these constructors directly and to pattern match against them. This makes sense for the option type, which is a well-defined algebraic data type whose internal structure should be known to the world. But if we were writing an abstract data type, such as a hash map or other data structure, we may want to encapsulate our implementation details. If we want to hide the implementation of a data type, we can declare it in the signature with the type keyword and neglect to provide a definition. In this version, the option signature guarantees that an implementing structure defines a type called option, but makes no guarantees as to its shape. Callers from outside the structure cannot call the type's constructors, nor can they destructure values of that type via pattern matching. The only thing an outside caller can do is pass that argument to a structure function that takes the correct type. In this way, we can abstract away implementation details and force users to factor through our public API that we control. Up to this point, everything we've seen is mostly standard fare from other programming languages. We have these module-like things called structures, which are optionally contained inside of other structures. Structures can choose to expose a public API while leaving other details private. And callers can access a structure either with fully qualified names or by opening the structure to access the names directly. Sure, the syntax might be a bit different than what you're used to in Rust or Python, but the core idea is the same. But here's the thing. Earlier, I emphasized that structures were a lot like values in some ways, including the ability to ascribe a signature to a structure in the same way we ascribe a type to a value. But in the value level language, a value can also be a function. That is, a value can take another value as argument and use that to compute a result. And structures in ML are no different in this regard. A structure that takes another structure as an argument is called a functor. And yes, the word functor means far too many unrelated things in far too many different programming languages. ML dialects use the word functor to refer to parameterized structures, which is what we're about to discuss. Haskell uses it in the category theoretic sense as a mapping from one category to another. C++ defines a functor as a class with an operator parens method that can be called as though it was a function. And Prolog uses the term functor to describe its base syntactic element, similar to the term S-expression in Lisp. All of that is to say, if you decide to write a programming language of your own, please don't make up yet another unrelated definition of the word functor. The poor word is suffering enough already. Anyway, we can define a parameterized structure in standard ML with the functor keyword. This is how we utilize ad hoc polymorphism in ML dialects. ML doesn't have an equivalent to Haskell's type class system, so if we want to make a function or data type polymorphic but require some constraint on the input data type, we use a functor. This is all a bit abstract, so it'll be easier if we just work through an example. A common data structure explored in freshman-level computer science classes is the binary search tree. A binary search tree is a tree where each node has at most 2 children, a left and a right. And the tree's invariant, which must always be true for all values of the type, is that if we have a non-empty node, then everything to its left must be less than the root node's value, and everything to its right must be greater. In our case, we'll implement a binary search tree that allows duplicates. So we'll loosen this rule slightly to state everything to the left must be less than or equal to the root node, and everything to the right must be greater than or equal to the root node. That is, if we have duplicate nodes in our tree, they may either be on the left or the right of the root. The benefit to this data structure is that all of the common operations are, on average, logarithmic time. Insertion, removal, and checking for containment are all big O of log n operations in the total number of elements currently present in the tree. Note that an unbalanced tree can drive the worst case to big O of n linear time. There are many tree balancing techniques that can mitigate or eliminate that problem, but for today, we're just going to write a naive binary search tree that doesn't do any balancing. The fundamental ask that a binary search tree makes of its element type is that it implement a total ordering. That is, in order to construct a tree containing values of type t, it must be possible to take any two elements a and b of type t and conclude that either a is less than, equal to, or greater than b. For instance, the tree shown here is over integers. Integers clearly have a total ordering. We could also define an ordering over strings, where they're ordered by their ASCII values. But it would be difficult or impossible to create a binary search tree whose values are functions, because there's no natural ordering on functions. So total ordering will be precisely the operation on which our functor is parameterized. Let's get started. First, we'll define a data type to use as the result of a comparison operation. A total ordering can compare any two elements and return a result of either less than, equal to, or greater than. So those are our three options. Next, we define the signature of a valid total ordering. A total ordering is an operation on a type t, which takes two values of type t and returns an ORD conclusion value. The name t is nothing special, it's merely a common convention for the target type of a signature like the one we're writing. Now we write a specific instance of this signature for integers. Doing so will allow us to create binary search trees whose nodes are integer values. There's nothing crazy here. Our compare function merely performs the comparison using standard ML ordinary operators that come built into the language. Now it's time to define a signature for our binary tree. This is what we promise to provide if the caller can give us a valid ordering. Specifically, we promise to provide a type tree and the type elem of individual elements. The former will, in our implementation, be an actual data type declaration, while the latter will be a mere type alias. But as far as our signature is concerned, as well as the rest of the world, they're both just types. On top of that, we'll provide a constructor for empty trees and three functions that operate on trees: insert, contains, and remove. Now we've made our promise. It's time to deliver on it. We define a functor called binary tree, which takes an ordering and produces an implementation of the signature binary tree. We call our ordering structure E, short for element. First, we define the type elem to be the ordering's internal type. Then we define our tree data type. As mentioned before, a binary search tree is either an empty node, which contains nothing, or a branching node consisting of a value, a left tree branch, and a right tree branch. The empty val is easy to write. An empty binary search tree, according to the implementation we just wrote, is merely a call to the empty constructor. Now we move on to the insert function. As a reminder, we're working in a mostly functional programming language, and in particular, the data type we're defining right now is immutable. So when I say insert, I mean we're going to construct a new binary search tree based on the old one, which also contains a new element. We won't be modifying any pointers in place. You could write a mutable binary tree with sufficient use of the ref data type, but the way we're doing it today actually turns out to be much simpler and nicer to work with. To insert a value into the empty binary tree, we simply place it as the root node. If the tree is not empty, then we compare the element we want to insert with the root node of the branch we're looking at. If the new element is greater, then by our invariant, it must go on the right. So we insert it to the right and leave the root and the left branch alone. If the new element is less or equal, instead we'll put it on the left. So we insert to the left and leave the root and right branch alone. Notably, in the case where the root is equal to the value, it doesn't matter if we go left or right, and in this case we simply have a left bias. By the way, the single quote at the end of ordinary variable names is not special. This is a common convention in ML dialects in Haskell, and it can be read as E prime, a modified or slightly different version of E. Our containment check is equally easy as a recursive function. The empty tree never contains any values, so if we hit the empty constructor, return false unconditionally. Otherwise, compare the root node against the element we're looking for. If the two are equal, we found a match and should return true. If the two are non-equal, then recursively call down to either the left or the right branch, depending on the result of the comparison. Now we need to talk about removal. The technique for removing a node from a binary search tree is not immediately obvious, so let's draw out an example. This is a balanced binary tree containing the numbers from 1 to 15. Let's imagine we want to remove the number 12 from this tree. The first step to removing a node from a tree, obviously, is to find that node, which we do using a similar technique to our contains function. First, we compare the target value of 12 to the root value of 8. 12 is greater than 8, so we move to the right. Now we repeat, and in this case, we've actually found our node. The root of our current branch is equal to the target value of 12, so this is the node we want to remove. Everything else we do from here on out will operate on the subtree whose root is the node we want to remove. Obviously, we want to remove the root node, so the value 12 is going to go away. But I need to find a value that can go in the position 12 was just at. Specifically, I want to find 12's immediate successor in the tree. That is, I want the smallest value in this binary search tree, which is strictly greater than 12. It turns out there's a very easy technique for finding that. First, we move one branch to the right of where we just were. The tree we're looking at now contains all the values in our tree greater than or equal to 12, and the smallest value in a tree is the leftmost value. So go as far to the left as possible until we can't keep going left. To summarize, the successor of a node can be found by going right once and then left until you can't proceed any further. In our case, the successor is 13, so move that value up to where 12 used to be. It's bigger than 12, so everything to the left of our root node is still clearly less than or equal to the root, since we made the root node bigger. And we specifically chose the next smallest value from the right tree, so everything else in the right tree branch must be bigger than or equal to the value we chose. Thus, the invariant of our tree is maintained. Note that in this example, our successor that we chose didn't have any right children, but for the sake of completeness, if it had, we would move the right branch up to where the successor used to be. Now let's write that in code. We're going to break this down into 3 functions in total: the public remove function and 2 private helpers. Remember that our structure can define any private helper functions it wishes, and since those helpers are not present on the signature, they won't be exposed to the outside world. First, we'll write a function called popSmallest. This function takes a binary tree and returns 2 values: the smallest value present in the tree, and the tree with its smallest value removed. This is what we use to compute and remove the successor once we've found our matching node. This is a private helper function, and I personally guarantee I'll always call it with a non-empty tree. After all, it makes no sense to try to remove something from an empty tree. So if we somehow get an empty tree, that's a programmer bug, and I'm just going to throw an exception. Now, in the case where the tree is non-empty, check if the left branch is empty. If the left branch is empty, we found our smallest element, so return the root and put the right branch back in place of the root. Otherwise, if the left branch is non-empty, recurse down into the left branch. This returns the smallest node and a new left branch. The new left branch will replace our old left branch, and we leave the root node and right branch unmodified. The second helper function we'll write is remove root. This is what we'll call once we've found a match and want to remove it. Again, it's a private helper, and I guarantee I'll always call it with a non-empty tree. So if we pattern match against empty, then throw a tantrum. Or an exception, whichever you'd prefer. In the non-empty case, first check if the right branch is empty. If the right branch is empty, then we're removing the largest node from the tree. There is no successor, so we can simply replace the entire tree with its left branch and call it a day. If the right branch is non-empty, then we get a successor by using our popSmallest function. We replace the right branch with the result of popping the successor, and we put the successor value back at the root of the tree. Now at long last, we write our public remove function. This is just a combination of the contains code we wrote a moment ago and the remove root helper. Specifically, compare the target element to the root. If they're equal, call remove root. If not, branch to either the left or the right side based on the result of the comparison. The only thing to note here is that if the value does not exist in the tree, we'll silently get the original tree back with nothing removed. Likewise, if the value exists multiple times in the tree, we'll remove one instance and not all of them. And that's a binary search tree. To instantiate this functor, we call it similar to how we'd call a function, except that we pass another structure as argument. So we can define a structure called intTree as the instantiation of the binary tree functor with argument int ordering. And we can call the functions therein like so. This is the true power of ML's module system. This is what the ML family of languages is all about. Polymorphism and abstraction come from parameterizing modules and then instantiating them at specific values. OCaml adopted a similar system and has been expanding upon it for many years. Agda's module system implements a feature called telescoping on top of this that allows parameterized modules to defer their parameters until a function is actually needed. And Scala is largely the final realization of ML's module system. Scala, between its singleton objects, path-dependent typing, and implicit resolution rules, implements the first-class module system ML developers have been working toward for, frankly, nearly half a century. And that's what I wanted to emphasize. The true benefit of ML comes from its powerful abstraction technique, which is based not on type classes or subtyping, but on modules, something we take for granted in nearly every other programming language. Next time, we'll be back to our normally scheduled programming with Project Euler problem number 32 in COBOL. See you guys then.